Ladies and gentlemen, welcome to another session here at the Paris Air Show. We are at the ESA-CNES stand. The rain has stopped, the visitors are coming in. Lunchtime has not come yet, so we're still in time for a fruitful debate, moving on from a sustainability topic to another one, actually, if you follow the previous panel. My name is Joanna Lung. I will be moderating this session entitled From Earth Science to Climate Action, Understanding Earth's Water and Carbon Cycles from Space. Now, we all know that Earth is a completely and complex and highly complex system, and we are just starting to, with our science, with the Earth science that we do, we are starting to uncover a lot of phenomenons. It really looks like the more we know, the more we want to know, and the more we need to know. So this is also what we're trying to see today here. We're checking on progress, on lessons learned, on successes, but we're also having an honest conversation about the gaps that we still have, the exciting missions that are coming up, and before we do a very deep dive into the science of the water and the carbon cycles, we have here with us on stage 4 speakers that will set the big picture and will tell us about the big trends that we are seeing in Earth observation at this moment. This is all so that we do the best science for those that need it the most, citizens, decision makers, all of us who are basically on the front line of the climate crisis today. So before we dive into the science, I would like to welcome first Josef Aschbacher, ESA Director General, Lionel Suchet, CNES Chief Operating Officer, Simonetta Kelly, ESA Director for Earth Observation, and Selma Kerkali, Head of the Earth Observation Program at CNES. As I said, they will set the big picture, and then we are going to move on with our Earth scientists into more detail. Josef, I would like to start with you. I have an opening question for you. Basically, we all know here that ESA is a leader in Earth observation. It's a example for other space agencies worldwide, and you have been also a director of Earth observation in your previous life, like we like to say it. And basically, you have seen some critical milestones from the birth of Copernicus. We just celebrated 25 years last week in Stockholm. The birth of our research and development and technology program, Future EO. So basically, now we are in a lucky situation where we have 4 decades of solid data that I believe give us great confidence to say what's next and what we should be doing next. And there are a lot of sectors in need of decarbonization that could actually help that could actually use our data. So, do you want to tell us a bit more about how we are accelerating this the space data into the non-space sectors and what's next, what's coming next in this crucial decade for climate action?
No, thank you. So first of all, I'm really happy to share this stage here with our friends and colleagues from CNES because we have been building up some of the major programs together. You mentioned the Earth Observation Program of Europe, which actually has several facets. Sometimes people only talk about Copernicus. Of course, Copernicus is the operational Earth observation program, and certainly a very, very big one, a very important one. But don't forget also the Earth Explorers, which are extremely important to complement the operational missions of Copernicus, provide science data, science knowledge to really better understand our planet, and therefore lead then to future operational missions in the Sentinel context of Copernicus, and of course also our meteorological missions, which are among the best in the world. We have just launched MDG in December. In the pavilion here, there are some examples of some of the first pictures of the MDG mission, top quality, and really altogether I think Europe can be very proud of having put together, having developed a very strong Earth observation program. And I think this is good, and this is nice to hear and nice to have, but it is also I would say, proof of how Europe can work together well. And let me just say really one word on this, because sometimes you hear Europe is very complicated, is very complex, very difficult, you have diverging forces, and all this may be true. And yes, Europe may be sometimes complicated and complex, but when we put our forces together, we really are almost unbeatable, very strong in what we do. And here we have put our forces together. The European Commission, the European Union through the European Commission, the member states of the European Union and ESA, of course the European Space Agency, EUMETSAT, and several organizations have really united on a clear, very clear program, and we have put together our forces. And in these 25 years, we have developed a gold standard program, and I think it is fair to say that it is very, very good and provides a lot of good data. So coming back, what do we do next, and where do we point? Of course, it's one thing to look at the planet, to take the pulse of our planet with our data and to monitor. This is absolutely necessary. And it's fair to say without this data, we could not understand climate change to the extent we do and do all the science. And I think this is fundamental. But we have to go one step further. And one step further means to use this data in connection with, of course, Earth system models, with high-performance computing, to develop digital twins where we can simulate our planet and therefore estimate what this simulation will bring and how do we go in the future. And this simulation, we call them digital twins, they are necessary to have what-if scenarios, so to have scenarios where you say, what happens if the climate is changing by one parameter? What happens if there's more deforestation? What happens if the temperature is increasing by not 1.5 degrees, but by 2.5 degrees or by even 4 degrees? And some of the scenarios do predict an even stronger global warming than what was demanded at the Paris Agreement. So what these scenarios, these what-if scenarios or digital twins are essential for scientists to simulate and see the extremes that can happen, but also for politicians to much better judge what decisions need to be made and what is the impact of these decisions on people. Because at the end, it always boils down to the population. What does it mean for people on the coastlines? What does it mean for people in the Amazon forest? Or what does it mean for people here in Paris or in France? Or if something changes in Brazil, for example, on the global forest or deforestation issues. So these twins, these digital twins, these what-if scenarios are fundamental, and this is where we have to invest in the future to, of course, feed them with data and observations on one side, but then really couple this with future modeling. We have done this in a small scale within Europe. A mini digital twin, if I may call it this way, has been established within the wider context of the accelerators. We have this with this concept of accelerators, which we have developed with our member states, which have been adopted in Matosinhos at an interministerial meeting, and then at the Space Summit in Toulouse last year. And that's a concept where we have a partnership which we put together with different partners who are concerned about the question. We have 3 accelerators that we have proposed and that have been adopted politically. First one is Space for a Green Future. Second one is Rapid and Resilient Crisis Response. And the third one is Protect, which we have just discussed before this session here. The one on Space for a Green Future really uses space together with those responsible for the decarbonization of the economy in order to help decarbonizing the economies of the various countries. Green Deal, net zero initiatives that you all know from the political discussions. We want to use space to help in this process and bring in those elements where space can contribute, maybe a small element, but maybe an important element in order to decarbonize our economies. So we have applied this one. We have started with a pilot phase in one small country in Europe called Austria, where we have used space data with other non-space data, simulated the various aspects, where to put solar panels, where are the best places for wind parks, where are the impacts of hydropower least for the population, how to transform one source of traffic or one source of transport into another one, of one fuel system or to another one, how to convert energy supply from one source to another in order to be more sustainable and in order to have I would say, the minimum impact for the population, because you have always to see how much does it cost and how do you impact people. And this is something that this little digital twin is allowing to do. You see, I think here, a small slide that is showing exactly that. We have released it in a beta version. Soon it will be released to the public. And of course, the hope is to apply this digital twin from a small scale or smaller country to more countries across Europe to meet the decarbonization goals of being carbon neutral by 2050 at the latest.
Thank you, Director General. And you have already hinted actually at my next question to Lionel, because we're now moving on to you, Lionel. It looks like in the last years, the philosophy of Earth observation is that, of course, we monitor globally, but we act locally. So the DG has already hinted at this, but I'm really curious how you put this in practice as a national space agency, how you contribute with your space program to other international European projects, but also how you cater to the national challenges. I'm thinking the fires in Gironde last year. I'm thinking sea level rise also for France, coastal erosion. How do you come up with more national-based solutions to problems that are in the end global, of course?
Okay, thank you for this important question. I will go from global to local via some examples on two important topics: is the water and carbon cycles we study from space. First, global. Space is a very special contributor to the global warming study because it gives us the unique opportunity to see the Earth as an object. It's very specific. Maybe when we are inside CNES, inside space, we don't see that because we are used to that. But it's very specific and very new, in fact, to have a tool to see the Earth as an object, not to see some very specific places. When you follow, and I will come back on that, on the rising level of the sea, you don't understand anything if you put some captors, some elements in some places on the Earth. You have to see it. You have to leverage everything at the whole planet. And the only tool for that is space. And that is why is so much important from a global point of view. It's a unique tool for that. How we can, as an agency, contribute to that? It has been said, and with ESA, we work at national, at European, and at worldwide level to develop new assets. I will come back on that also, because you have a very strong effort on that. And it is important also, as mentioned Joseph, we have to work together to develop new tools to extract from these data, which are more and more numerous, very specific elements, services to people. And that's also an important thing we have to do together. Joseph mentioned the digital twins. We have in France 2030, which is a global tools to develop services from data, from space data, to develop services. This morning, I signed a contract with the Kairos Society to tackle fire risk from space data, and now we can go into such details, and it's very important for us. Now, some example about space assets and what we do on two important things. First, water cycle. And to better understand the water cycle, we developed together with JPL, NASA, in a bilateral agreement with contribution with the Canadian Space Agency and the UK Space Agency, the satellite SWOT. SWOT is an acronym for Surface Water and Ocean Topography. It's based on a major disruptive technology, and the satellite is able now, already in space, to measure surface water levels with incredible precision, and will clearly be an important asset for the development of blue and green economy, with application related not only to the ocean and the coastal monitoring, but also to the continental hydrology. So not only the sea level, but also the lake and the big rivers hydrology, and so fresh water management, which is very important for our future. Several other missions will be later developed by Selma, also dealing with the water cycle. The next mission we have is Trishna. But for sure, the work we make together with the Copernicus programs is also very important for that. And we are working hardly with ESA on this project. About carbon cycle now, which is another very important topic to study global warming. We developed after the last COPs on this domain, we developed two major systems, microcarb on CO2 measurements in partnership with many French laboratories, but UKSA also. And Merlin, we developed for methane measuring in cooperation with DLR, Germany. And they will be launched respectively in 2024 and 2028. And those data combined with other measurements will also study the carbon cycle, which is very important. But the challenge now is not to acquire more data, and then I go from global to local, but it's also to show to the people about and to the politician what is the real impact on their places about global change. I can't tell you that an average on the planet is the sea is rising 3.2 millimeters per year in an average of 30 years, which is true. Now we are more about 5 to 6 millimeters per year. But okay, it's something we can consider as a concept. But this I say to you that within 5 years we have no more house because it will be underwater. It's something different for you, for your point of view. And then we go to local. And this is exactly the role of SCO, the Space Climate Observatory. We reckon with ESA to use space data not only to study as a global way the system Earth, but to study very locally, with very concrete chantier, what is the impact of the climate change to very specific places. And that's very important also, and it's very local. But going back to global, what is very interesting with space, when you have this very local application in one place, you may use it to have local application in everywhere in the planet, in another cities, for instance. And when you study problem of flood, problem of risk of fire, and when you have the tool to locally deal with that, with space, you have also the capacity to globally deal with that. So you see this share between global and local is both very important, and both very space can answer both globally and local these problems.
Thank you, Lionel. And I know for a fact that we're coming back to SWOT, we're coming back to SCO. So indeed, Selma and Carol will give us a bit more detail on that further on. Before they do that, I would like to pass on now to Simonetta. And Simonetta, you have been taking the lead in Earth observation from Joseph. And a lot of the experts are now saying that basically we're living in a golden era, the golden era of Earth observation. So this comes with opportunities and with challenges, of course. A lot of users, a lot of applications, solutions, but also new needs, new gaps that are identified on a daily basis. So as a director of Earth observation for the European Space Agency, how do you organize this future architecture of the Earth observation system that we have the best results also in the years to come, decades to come?
Thank you, Joanna, and good morning to everybody. Yes, it is the golden age, as Joseph said, of the Earth observation. Today, just to give you a few numbers and put this in context, we have 15 satellites at the European Space Agency in operation in Earth observation, more than 40 in development. And these are on the free lines of meteorological program with the EUMETSAT, of course, the line of Copernicus with the Sentinels, under the leadership of the European Union, operational mission for long-term continuity of data to support real user requirements, and then the science mission. And this golden age of Earth observation would not be here today if we wouldn't have developed research missions at the start of it. And there we think of the precursor ENVISAT, ERS, and missions like that, which really paved the way to today being able to have an operational system like the Copernicus one, which is really the reference system worldwide in terms of data provision, number of satellites, and diversified instrument offer to support different policies. How do we work on the user requirements? So we don't just work on a technology push approach, which was maybe at the very start of the space business overall, over 60 years ago. We work really on user requirement basis. And those user requirements we collect, for example, for the Copernicus mission, the Sentinels, but also the next generation expansion mission, which are coming up soon, hopefully, based on requirements which we collect through the European Union. Typically, we started with the first generation Sentinel mission, but the one now we are developing, the expansion mission, has enhanced user requirements which come from dedicated policy sector, go from the agriculture sector. So there we have a mission called LSTM, which looks, for example, to support all what is related to agriculture policy. We have the CO2M mission, which is going to step after microcarb as a research mission, as an operational one. So very strong collaboration there also with the national mission, and that's why we're here together with CNES, because the collaboration is really close there, and not just on this one. But we also get requirements, for example, for the Arctic policy, and there you have Crystal, which is a follow-up of a science mission like Cryosat on altimetry. So the requirements are collected through various means. Of course, the European Union is a key partner for doing that, but also EUMETSAT is very important, and we have a very strong collaboration there. Via EUMETSAT to the requirements coming from the Met offices, and there I think of the ALUS 2 mission coming up in the coming years, which is based really on requirements also coming from Met offices. And then, of course, last but not least, the science community, because you always need to have enhanced innovation, technology, instruments on board the satellites, and you also need to have systems that actually pave the way for future operational missions. So that's how we get organized. And typically in the context of UNFCCC, we got requirements from the system related to the climate variables. So those 50 climate variables which are associated to the United Nations climate environment setup, the UNFCCC, we can support to over half of those variables with space data. So those requirements, in addition, come from the international community through the UN setup.
Thank you, Simonetta, and I am going to pass to Selma now. Selma, I actually have a similar question to Simonetta's, but again, we're going back to the national level. So how do you organize your work and your collaboration with other space agencies in the international context, in the European context? How do you decide which missions to contribute on, which gaps you want to fill and can fill? How's your thought and decision process on that?
Good morning. First of all, thank you for this question. I'm very pleased to be here today also with ESA. I think, first of all, within the emergency of climate crisis, since the creation of the French Space Agency, the DNA was really the Earth observation program. And the main driver to decide which programs have to be implemented is related also to science community, as mentioned by Simonetta. This is really important. The needs are really retrieved from the science community. And the Earth observation program within CNES covers all the facets from those needs to identify the gaps, the needed observations, and of course all the key actions behind that. From the preparation of the future with the key research and technology development, but also moving towards also the preparation of the applications behind the science-based observations, of course. And that's why the international collaboration and European cooperation from the beginning and from its inception is really also a key driver. Science needs, the international cooperation, European cooperation, and two principles which drive really the Earth observation program with CNES is the subsidiarity and the complementarity. We are not doing what is already developed and implemented either at international level or at European level. Our main driver is research and development missions that could be precursors for the, other missions at the Copernicus level. And of course, if we move to Met Office, CNES also has used to develop many operational meteorology instruments to be on board Met satellites at Metopes G and so on. So, of course, this is the background. But the space context is really evolving. And we see that from the huge amount of data we have today, as mentioned by Lionel, we have also within the national level, what we call the France 2030 program, we have a new generation of new entrepreneur, startup, who also are proposing new potential services and also data which could be complementary to the science-based mission, which are, of course, required due to the climate issues. And if we could give a broad picture of this program, as I mentioned, of course, science is a key driver. Innovation is another one. We are not developing a recurrent mission or operational mission, but also build what could be tomorrow sustainable in another context, Copernicus, Europe, or at international level. And of course, when speaking about climate change and science, behind that, of course, there are societal, of course, questions and cooperation. Here, just a few examples. Of some space missions which are already in collaboration, like MicroCab, mentioned by Lionel, and it's really the first carbon European mission as a research mission, and already there are many partnerships with ESA, but also with EUMETSAT. Namely, MicroCab will be, of course, a key contributor to the CalVal of CO2 emission, for example. Trishna, Simonetta mentioned LSTM for agriculture purpose, but Trishna is a long history in France. For more than 20 years, the science community has identified a key unknown processes related to water cycle. And they propose several times this important mission, which is now under development in cooperation with the Indian Space Agency, ISRO. And so we will come back later on that. And as mentioned also by Lionel, I think having all those data is really critical and important. But France has proposed this Space of Climate Observatory. As mentioned by Joseph, it's not only for monitoring, understanding our changing Earth planet, but also how could we predict at the local scale and at the right scale at the population level. And this is just a snapshot where we see today the success of this program. Now I think there is 38 members recently signed during the GLOC in Oslo, and many projects around the world.
Thank you, Selma. And I know our high-level speakers are needed and wanted in many different places, so I won't keep you much longer. I do want to have a final follow-up question to Simonetta, because we were just in Bruges for 2 days with over 200 scientists as part of a very user-driven process of reviewing the science strategy for Earth observation. And I think you can give us some conclusions à la chaud, I think we say that in French, on what the science community needs most and what we need from them also.
Thank you, Joanna. Yes, we were split between the Bourget and Bruges, where we collected the inputs and advice from over 200 scientists from Europe to prepare an updated Earth observation science strategy. We will use this as the reference to prepare for the proposals for the ministerial in 25. What we got there, it's of course many different opinions by different scientists on what we need and what is top priority, so we'll have to do a synthesis of that. But clearly, what it was an important message is that today's science is not just done for science, but is done to relate very closely to societal challenges. And those challenges, of course, include the climate change challenge, but include also water resources management, include issues issues which are really on top of the agenda for everybody, and they're associated to food security or issues that are really for citizens very valuable. So I think that's a new dimension of our science approach that we're going to take in the coming months and consolidate before the ministerial.
With this, I would like to thank our policy, strategic, high-level speakers. Thank you, DG Aschbacher. Thank you, Simonetta. Thank you, Lionel. Selma, you're staying with us for the next part of the panel. We are now moving on to the science deep dive. I would just like to invite on stage. I would like to invite on stage Craig Donlon. He's a head of in the Earth Sciences Division. Carole Daniel, there she is, atmospheric science expert with CNES, and Yashka Meyer, mission scientist for the CO2M mission at ESA. And here, Selma, will have some time to come back to your slides because I know we skipped some. Before we do that, I would like to start with Craig now. And of course, for everyone that has been reading the news, recently, I'm coming with the slides, Craig. El Nino has been making a lot of headlines. We saw some signs, pre-signs, warnings, pre-warnings, and all the signs point to a substantial, to an impressive effect for El Nino this time around. So it's a highly complex process with a lot of consequences for actually the whole planet. So I think it's a good example to talk concretely about how we look at these complex phenomena with a multitude of insights, with a multitude of missions combined together. And this is where the insights become really, really powerful.
Thanks, Jana, and thank you for inviting me here to talk. What you can see on the stage here is a beautiful rendition of the El Nino and La Nina signals. La Nina in 2022, you can see the cold blue anomalies there. And these maps are made up of multiple satellite data and in situ observations with the beautiful mesoscale characteristics. You can see the huge signal from El Nino stretching across the Pacific Ocean, which is the biggest signal that we have on the planet today. Now, you can only get a grip of this from space. We can see it here in sea surface temperature, but you can also see its signals in altimetry. You can see a height change, a steric height change from this feature. There are biological implications, of course. But what I want to draw your attention to is if you look towards the Atlantic in the 2023 image, it's warm. If you click through there, Jana, we've had a sustained high-pressure system sitting over Europe. The Azores High is extended. The polar vortex is putting this and keeping this system there. And you can see here extreme temperatures. This is a marine heat wave that we have around the coast of the United Kingdom. And of course, the heat is pouring in through clear skies. Not today, unfortunately, but most of the time, we've had beautiful clear skies. And remember, towards the top of Scotland and into Norway, we have 24 hours worth of sun. So we have continuous heating, low wind speeds, there's no mixing taking place. And we see now a Category 5 marine heat wave in the North Sea and around the coast of Norway. Now this is important because it's a miniature tipping point. That means that there can be destruction to the ecosystems in this region. We will see afterwards. But remember, in a climate sense, if we achieve one of these tipping points, the time series that we have from space and from in situ before will be different. So if you click through to the next one.
I want to ask you also, Craig, what happens when how far do they travel, these marine heat waves, and what happens when they get up north, where we are in the very delicate environment of the Arctic region? What do we see there?
So, I mean, if you imagine the heat that you've just seen on the previous slide, eventually when the winds pick up, that will be mixed into the water column, and some of that heat will find its way through the Fram Strait and the Norwegian Sea into the Arctic. And here we're intensifying the Arctic. We talk about Arctic amplification. And this is a quick graphic that shows one version of that. We have CO2 that's warm in the atmosphere, which Yashka will talk about CO2M as a mission. We can see the meteorology from space from our meteorological satellites. Here you look in the polar vortex. We monitor sea ice from space and we can see a decline. And remember, if we have less production of thick sea ice, we produce less heavy brine water. Sea ice is fresh. When you produce less heavy brine water, this normally sinks to the bottom of the ocean, driving the thermohaline circulation. If we don't have that, we're changing global ocean circulation patterns. If we carry on round the circle here, the biological signals are impacted by a change in fluxes of temperature, of salinity. We also have to think about the wave climatology in the Arctic. Now we will be opening up the water surface to the wind. We will be creating waves that do not normally exist in the current climate. Moving further on, we start to see melting permafrost due to the heat that's going into the system. This has drastic consequences for the people that live in that area, but also we can have the great potential and grave potential of releasing methane into the system, excavating the whole thing. So you see a really vicious cycle here. Arctic amplification is something we have to worry about. I was recently in Svalbard, and you can see the changes taking place in that area. I went the year before, and the glaciers have retreated 30 meters. It was remarkable to see on land. So there is a real issue here.
Craig, before we move on back to Selma and we talk more about the water cycle with you, Selma, I have another question again, because we were talking with Simonetta about the future. So I want to do the same imagination. Well, it's not really imagination; it's half reality, because they're half built. I want to talk about the missions that we are building at the moment and will be operational in a few years, and how that is going to give us a much better insight, let's say, for the next exceptional El Niño in a few years.
So what you see on the screen here is the so-called expansion missions for Copernicus, where we've taken user requirements, policy-driven, as discussed earlier, to develop a cutting-edge set of satellites that work together for a variety of different policy-driven areas. Climate change and mitigation of climate change is important. Food security is important. Monitoring land and natural resources. And of course, sustaining the Arctic and understanding how we can mitigate the changes of all of these different issues that we face. And the water cycle is very much at the heart of this. So for the CO2, we can understand the driver, how we are heating the atmosphere, what's leading to a warmer atmosphere. LSTM, the Land Surface Temperature Monitoring satellite, here we'll be monitoring the surface temperature at fine spatial resolution, and together with other satellites, Sentinel-2 in particular, we can look at heat stresses. This is gearing towards understanding food security. With Crystal, a dual-channel altimeter, and the Simmer, a workhorse for operational activities all over the world, where we can measure the surface emissions in the microwave. We have an unprecedented capability to monitor the demise of the ice in the Arctic, and also to monitor changes in the ice sheets. And of course, gravity and measurements of our Earth's gravity field sit at the very heart of many of these things. The great integrator is gravity. So the next generation gravity mission has many facets and features that will allow us to understand some of the fundamental changes of mass and the mass distribution, of which the hydrology cycle is super important. And here we'll be working together with two pairs of satellite-to-satellite gravity missions at slightly different orbits, a part of the Mass Change in Geosciences International Collaboration, Constellation, with NASA, to put together a gravity mission that will have unprecedented capabilities, a true integrator. So I think the future is super bright, and we have fantastic missions, always remembering that whatever the background to a satellite mission, every measurement is a scientific measurement, and science will find a way to use that data to the best of our ability.
Thank you, Craig. And now we're coming back to Selma. The name SWOT, the acronym, the mission name has been mentioned a few times already. Of course, it's a very important mission for the water cycle, and the results we have seen recently, the first results, because you launched at the end of last year, the first results are absolutely spectacular. So, Selma, I would like to hear a bit more about SWOT, the do-it-all water cycle satellite that looks into ocean, rivers, lakes, and all water bodies across the planet, but also the other suite of CNES missions that look at the water cycle.
Yeah, thank you. Thank you for the question. Perhaps before responding about really the added value of SWOT and the new era that is now being open due to thanks to this observation, I would like just to remind that within the climate change, it's really impacting strongly the water cycle. And the scientists have already highlighted the fact that we are missing, really many key processing in terms of understanding what is happening. What is happening in terms of extreme events. We have some floods in some parts of the world. We have some drought in other parts. And we don't know where it comes and when it is going. So that's why the water cycle in terms of research activities really is a key topic. And given the example by Greg on the Arctic, and given the complexity of the Earth system, today the new challenges is how we could have an integrated approach between the water cycle, understanding also the carbon cycle and also the energy cycle. This is really the way that the research will be advanced for the future years. So Simonetta speaks about the updated of the European EU strategy. I would like just to remind that every 5 years in CNES, we have a regular scientific seminar perspective, which is an important rendezvous with the community in order to update the roadmap and to identify the new gaps. So why I'm speaking about that? Because in the Science Perspective Seminar in Biarritz in 2009, the science community, not only the ocean one, who is used to work with the altimetry traditional Nadir mission, but also the hydrology community, the land community, recommended to CNES and to NASA through the Decadal Survey to implement this really breakthrough mission. This is really breakthrough because it will help us to understand the full water cycle thanks to the firsts of all water surfaces, meaning river, lakes, reservoirs, at an unprecedented spatial resolution, which means at very fine scale, and delivering other important observations such as height or slope, which will allow us to develop what we call discharges, which means we will understand the dynamics of the waters. And this is really the important and the graal for the hydrology. And understanding and having those observations will allow also to develop, and this is undergoing, a new generation of models in order to have a prediction of discharges. This is for the water aspect and land, but for ocean, it opens a new era and a new vision for ocean, because it is providing observations 10 times better in terms of scales and the resolution than the current technology, which means that we are spanning from 100 to 10 kilometers in terms of resolution. If you come back to the previous slide, please. You will have a two-dimensional images instead of Nadir profile as we used to have today, of course, with Copernicus mission for a long tradition of this historical Nadir altimetry field. And on the left side, you see one of the first images delivered by SWOT on ocean. And speaking on some important climate effects such as El Nino, here I'm pleased to show for the first time on the right scale a dynamic of El Nino delivered and monitored by SWOT within the fast sampling phase of 1 day. And this is an animation of the Gulf Stream dynamic, which is observed by SWOT. But SWOT will also, next slide please, will also deliver, and it was not really awaited at this early stage of the operational of the mission, with this unprecedented precision of 250 meters, which is better than the 1D altimeter. You have on the right scale, you have the coastal images, which is perfectly fitted with Sentinel-2 images, which show also the bathymetry and extremely sharp topography gradient. So it's really, the community is really waiting the data, which will be delivered after the science team meeting, which will be held in Toulouse in September, It is aimed to be delivered in October for the global community in open and free. And of course, this mission working jointly with the ESA is preparing also the next generation of Sentinel-3 topography mission. Of course, it will be not SWOT-like. Greg always reminds me this. But in the meantime, we agreed at the program board that we are moving from Nadir altimeter generation to a new generation mission. We are very excited at European level. Already we are working jointly and closely with ESA to prepare also this next generation mission, which opens the door to many. But if you come back to this slide, which is not complicated, because you mentioned NGGM, you mentioned many Copernicus missions, and in the meantime, I would like to remind that there are still key processes in atmospheric component water cycle. That's why, for example, CNES is a partnership with NASA for the next generation of ATRAIN and global precipitation measurement, which is called AOS, Atmospheric Observing System, where we learned from the science community for the last decades that we are moving from precipitation era to convection era, which means that we need to understand those extreme events that I mentioned in the beginning, typically in the tropical regions where we know that the storms are really not very well known, where they are coming from, and how they occur, and how they disappear. That's why CNES is contributing here also with the train of two microwave radiometer in order to better monitor those convection, deep convection processes, which are new. We are not, in fact, at the end of the history. And just to mention that, of course, we have many data today. Trying to tackle this water cycle budget. But be careful and be aware that all those data are not at the same spatial and temporal resolution, which means that at national level, but also at the European level, we are developing between those assets of space data, models, and other in situ data, a way to integrate all those assets in order to make the prediction of the water cycle in a different, of course, area. And I would like just to mention that CNES, I think since now 20 or more 20 years, we developed Megatropic with ISRO dedicated to a key component for water cycle. We developed, of course, the Nadir altimeter moving to operational and Copernicus services and operational missions. And we continue to invest and to develop and support the community in order to really reach the accuracy that is needed for those key components of water cycle. That's why we have some similarity between Trishna and SWOT. Both, of course, are multilateral program devoted to water, to ocean, and to coastal. And they are also precursor to the Copernicus context, like LSTM for Trishna, already many project activities at a different level, science, mission, and Copernicus, and Sentinel-3 and GTOPO. But it's not the end of the history, because besides and thanks to this program, we are also supporting the preparation of downstream applications, relying on the best of science evidence.
Thank you, Selma. I'm a bit conscious of the time, so I would move on to the next cycle that is keeping our scientists busy, and that's the carbon cycle. So starting with you, Carol, again, a name we heard before, that's microcarb. For those of you here in Le Bourget, there's a model outside that can be admired in real time as we finish this panel. So CNES will be launching microcarb. It's a mission that's looking into carbon sinks and sources. And here, again, in theory, the maths seems quite clear, right? The things are absorbing more, and the sources are emitting more, and that's that. But here we really have the devil in the details, and a lot of research and a lot of new findings coming out every single day. So can you put a bit more nuance on this science of sources and sinks, and can a sink even become a source, or the other way around? What are we looking at the moment?
Yes, it's a really complicated picture. And first, it's important, and it's very important, especially here, to talk about carbon here at the Paris Air Show, because I think it's a very big challenge for us. As you all know, CO2 is the main driver of the global warming. Each year, there is 40 billion tons of CO2 which are emitted by the human activity. You can see here the big part of this emission are due to anthropogenic activity, which means fossil fuel combustion, land use change. And for that, we try to keep the count of this emission every year, because it's what creates this global warming and the climate change and all the impact that we know each day, as you say in the information TV. Hopefully, so first, since the pre-industrial activity, we the CO2 enhanced by more than 50%. 50% in the atmosphere, which means that it's the main driver for climate, as I said. There is also another powerful greenhouse gas, which is methane, which is also very important for the climate change. These two big greenhouse gases account for more than 80% of the cause of the climate change, which is very big, and of course of the global warming. For that, all the governments agreed to do something, to act in order to limit this big challenge for humanity and the planet. There is the Paris Agreement, which was signed in 2015 to limit this emission. But there is a lot of science also which is needed behind that, because if we know who emit and where, we need also to understand what are the things which limits the impact of this emission. You can see here that all the exceeding CO2 which are emitted by the human activity are also absorbed by the natural ecosystem. Half of that is absorbed by the ocean or by the land, the vegetation process. The rest, almost around 48%, which is the next slide, please, stay in the atmosphere, and it is the cause of the global warming. So we want to stop that, and for that we need to measure, to monitor how the sink will react to the climate change, because the deforestation, the enhancement of the temperature in the ocean will create some change in this sink. And if these two important sinks, which absorb the exceeding CO2 in the atmosphere, stop pumping the atmospheric CO2, then we will have another big problem for the future and for the climate. So it is really the two big important facts that I wanted to show first. It is the GIEC, the International Scientific Panel, which have this status. It's not us, it's not the Space Agency, of course, but Space Agency now need to try to propose a solution. For that, at CNES, we had the microcarb mission. After the Paris Agreement in 2015, the French government decided to engage this process to create a satellite to bring some observation of this CO2 in the atmosphere and how it will evolve in the future. It's a very small satellite. You can see again the model just here. It's an instrument which is less than 80%. All the engineers in space really try to do the best to propose a solution. And with this innovative instrument, which should be in space next year, we will deliver some new information to really answer some question about the sink, how the sink reacts to the global change, and where in the planet, and how the politics can also act in order to do the good regulation. It is a very big challenge because we need to measure the CO2 at a very, very, very big precision. We need to measure the atmospheric CO2 content with a precision better than 0.2%, which is very, very challenging, and all the engineers know this challenge. It is a very strong precision. This project is possible with a lot of cooperation with especially the UK Space Agency, EUMETSAT, and ESA also. And it will really pave the way to create some expertise in Europe, also to prepare the arrival of CO2M, which is the more complex instrument in space to bring some new answer again on CO2 and methane. So I think it's very important that space propose some solution in order to act. And finally, the last slide is just to talk one word about the methane, which is the other greenhouse gas, which is responsible for the climate change also. The methane is interesting compared to CO2 because it's a greenhouse gas which is much more powerful than CO2, but which is less abundant in the atmosphere. It has a lifetime of 10 years compared to CO2, which is 100 years. So we have more possible action, more quick action to reduce and to mitigate the climate change. At CNES and with the cooperation of the German Space Agency, we propose this Merlin space mission, which will use a laser to try to quantify also with a big precision the methane concentrations in the atmosphere. And it is, again, also here a very scientific challenge. But it is also a very big, important asset for the economy because, of course, science guide and drive what we should do. But of course, the economy and the society needs also to act together with the scientific proposition.
Thank you, Carole. And you already hinted at this, but now it's time to focus a bit more on human-made emissions with Yashka. And here again, we start from a mission that's in preparation, that will be launched quite soon. It's one of the 6 Copernicus expansion missions that are the logic of these expansion missions is, of course, that we identified, since we launched the first fleet, we identified some pressing needs and gaps that have to be filled with this new generation. So tell us more about how we are measuring human-made emissions compared to what Carole has mentioned about all the natural processes. Why is this important? And we'll be launching in the second half of this decade. We have the global stocktake now this year, the first one. We have another one in 2028. So I'm going to ask you the difficult question. Are we too late? Are we still on time?
Thank you, Joanna. Yeah, there is certainly a crisis, so we also need to act in a crisis way. With the Paris Agreement, we are trying to tackle the climate crisis. And maybe the DG started to talk about the 1.5 degree. This is global mean temperature. And if you would put it more in human timescales, if you would have put on a jacket at the beginning of the talk, and maybe a jersey and maybe another coat, you would start to feel warmer and warmer and warmer. And this is exactly what is happening with our atmosphere. We have CO2 that is being added. It's a greenhouse gas. You know what a greenhouse is doing. And methane is like wool. It's holding the temperature even more to you. And nothing changed to your environment. Your environment is unchanged. You just put on more jackets. That's what's currently happening with the atmosphere. So very happily we have the Paris Agreement, and it's an honor to be here close to Paris, where this was all signed. And we have also a CO2M model next to microcarb, so it's very nice to be here next to each other. So CO2M will focus more on the human-made part. And if you look from space, you will see both. You cannot see only one of them. So in order to be able to zoom in on the human part, you need to be focusing a lot more on where this is coming from. And this is exactly what we need to tackle. So we need to tackle it at the local scale, from power plants and cities, and more at the national scale, because we want to be at the zoomed version, but also the bigger picture, because we need to, in the end, is counting what is in the global atmosphere and what is heating up our atmosphere, and then finally also causing problems all over the world. And maybe just one small highlight, we're talking about global mean temperature. It doesn't mean that everywhere the effect is the same. We have seen the example of the Arctic, where things are going much worse in a more rapid way. So one of the tricks that we are doing is actually by looking also to co-emitted species. So if you burn any fossil fuel, there's a lot of nitrogen in the air. If you burn nitrogen in a high temperature, it will also try to burn basically, and you emit NOx that is converted in NO2. So we're also measuring NO2, but that's not giving us an immediate handle on the quantity of CO2, but it's giving you the location of the plume, which is very important. And maybe if you can see in the noise where the CO2 is, you know exactly from NO2 where to look. And already mentioned, we are looking at 0.1% changes. So if you would look at, I always compare it to your bath. If you have your bath, you put your shower head under the water, you see a little ripple. That's what we're trying to look at. On top, we have these nice kits that are in your bath making waves, because nature is making a lot of waves. Nature is absorbing and re-emitting CO2. And on top of all of that, we try to see what is coming out in terms of human emissions. So it's very difficult, but we're aiming to do so in a very challenging timescale. We have benefited a lot from previous developments in the whole program that Simonetta has been describing. So we have really on top of the developments, we have even added more elements that are contributing to an even better mission, and people are really looking forward to see the first data.
Thank you, Jaska. And I do want to continue the conversation about methane as well, also a powerful greenhouse gas. And here also we've seen a lot of initiatives, international initiatives recently, the Global Methane Observatory, the World Meteorological Organization saying that they want to mobilize and measure this better. So, and it really looks like it's also a low-hanging fruit in the sense that maybe it's somehow easier to deal with this, but also it's a bit of a win-win because even the commercial emitters want to know where their leaks are. So you have a very clear also business case for them. You're actually helping them fix their problem and avoid losses if you identify the methane leak. So it's win-win for businesses and for the planet. So how do you see our fight against methane emissions going?
Yeah, thanks. So I think it's important, like you say, you're not deliberately emitting methane. I mean, it's really coming from leaks, unintentional leaks. While CO2, you're burning something, and in that process, you're releasing something. So if we just step back to the Paris Agreement is actually relying on self-reporting. So we were looking at what we call bottom-up. So nations look at activity, how many cars are driving around, how many fossil fuel went into the country and is burned. For methane, it's the same. So we rely on companies to report their own leaks, and they're not very good at it. So what we see from space is actually much more. So we see much more methane from space. And if I can give an example, which is a bad case, but also a good case for Earth observation. So from one of our satellites, we've actually seen within the Copernicus program that there's a lot of methane coming out of Turkmenistan. It's an oil and gas rich country, and in this process a lot of methane is going into the atmosphere, which we have seen from space. And it's actually recently resulted in an agreement that they're going to take measures to try and reduce this. So I think this is really a success story of Earth observation, trying to curb methane. Methane is a very potent greenhouse gas, and like I said before, people do not want to or should not want to emit it, so we can actually put policy measures on top of this.
Thank you, Yashka, and I would really like to reward everyone here who's skipping their lunch to be with us and participate in the debate. So as a reward, I would really like to expand the panel for 5-10 minutes and have a bit of a Q&A round. So I'm looking at my colleague with the microphone, and I'm also looking for a show of hands if anybody wants to. I know you were not prepared for this part, but if anybody has a question for our excellent scientists and wants to take advantage of them being here with us, I would like to open the panel for questions. I don't see the hands though. So I'm just going to assume you will kidnap them when we are done with the official. When we are done with the official discussion, I think you're going to kidnap them and
Joanna?
them. Yes.
If I can give one more comment. So
Yeah.
I think one powerful thing of Earth observation is that we can visualize things. So, and we can do it globally in a very consistent manner. But in the end, we rely on policymakers and you, the people, to take action on what we are seeing. So we cannot take that action for you, we can enable it. And that's what we are developing all together.
Thanks, Yashka, for passing the message. And since I don't see any hands, I would like to go back to Craig. He's going to wrap us all up. And until now, we've been talking about the carbon cycle, the water cycle, going a bit back and forth. But obviously, it's all interconnected. So, Craig, just conclude and wrap up the panel and tell us how it's all interconnected, and we'll be on our way with the panel. Thank you.
You put the last slide on. I think what we have to remember is water is an amazing substance. I mean, we're all made of water, largely. There's water outside. But 75% of our planet is covered in water. It's the buffer for climate. And all the measurements that we've discussed here, the fantastic measurements from SWOT, the wonderful measurements of carbon, the precursors to the CO2M, plus the thermal infrared and the Copernicus, the microwave, the active SARS, they're all working together to get a picture of our planet. 25% of the carbon dioxide in the atmosphere today goes into our ocean. And our ocean is 75% of our planet, but it's not the dumping ground for everything. It has a capacity. We can only go so far. And as the carbon increases in the ocean, so does acidification. And with acidification comes species and ecosystem changes. Ecosystems cannot survive. Bear in mind that many millions of people around the world rely on the ocean as their major source of protein. So we face a real existential crisis here. We've shown you the warming. We've shown you the amount of CO2 that's going into the atmosphere. And when we combine Earth observation, we can see areas where CO2 is going in and where CO2 is coming out. But as Yashka says, we can bring you the evidence. That's what we do. We bring the evidence base on which policymakers can set policy, the evidence base to which policymakers can monitor the impact of their policies, not just in Europe, but across the world. And this is fundamental. The change, that has to come from all of us. We need to change our style of life. Otherwise, the consequences could be quite severe. Earth observation is here to help, but let's not forget to listen to the message.
Thank you, Craig, and thank you, everyone. I think the call to action is quite clear. Thank you for joining us. Thank you for those that have been following live on ESA Web TV. Our experts are staying onwards. We have more experts coming in also for the Public Education Day, so we're here with you until Sunday. Drop by, come and ask us all the earth science questions that you want to ask us, and follow CNES and ESA websites for news and new research, new science, new technology, and all things space. Thank you.